Let me introduce our first speaker, Bonnie MacCulloch of CPS. Bonnie is a regulatory scientist with Critical Path Services, CNOL. She supports pesticide registrations under FIFRA, environmental risk assessments, ecotox study monitoring, and seed treatment technology. Prior to joining CPS, Bonnie worked with both federal and state agriculture agencies, universities, and industry partners in the area of integrated pest management, plant protection, and entomology. Bonnie has her master's degree in environmental forest biology with a concentration in entomology from the state of New York College of Environmental Science and Forestry. Bonnie will be presenting background on seed treatment. Bonnie?
Thank you, Julie. So as Julie mentioned, I will start off this hour by talking about what seed treatment is and a little bit about the history of seed treatment. My presentation will be followed by Amanda talking about the seed enhancement evaluations and Paul following up with analytical tools for seed treatment. So what is seed treatment? Seed treatment is a tool that is used to protect a seed from damage caused by pests and pathogens. Seed treatment can be further defined as the application of fungicides, insecticides, and sometimes biological agents applied to seeds to suppress, control, or repel plant pathogens and pests that attack seeds, seedlings, or young plants. Additional amendments such as inoculants, micronutrients, polymers, and colorants are also often applied in combination with the pesticide. The application of these products in some combination is applied to seeds using a slurry. A slurry can be a single, ready-to-use product or a combination of several seed treatment components mixed with water and added to seeds. Specific components of a seed treatment are considered pesticides under the Federal Insecticide, Fungicide, and Rodenticide Act because they are intended to prevent, destroy, repel, or mitigate pests and pathogens. EPA is required under FIFRA to ensure that a registered pesticide will perform its intended function without unreasonable adverse effect on humans and on the environment. In the Code of Federal Regulations, 40 CFR Part 150 to 189, you can find the registration requirements, including specific data requirements that all pesticides must meet. These data requirements are intended as guidelines that serve to evaluate the efficacy of a product that is intended for registration and to demonstrate, again, that no unreasonable adverse effects will occur. Products intended for use in treating seeds must also contain an EPA-approved dye. The purpose of the dye is to impart an unnatural color to the seed to signify that it has been treated. The use of seed treatments to protect seed was one of the first crop protection measures to be practiced today. Seed treatments continue to evolve with the development of new technologies. Seed treatments offer benefits for growers in the form of effective control against below-ground pests, such as those pests that cause seed rot and damping off, and from above-ground pests that affect seedling development and cause foliar damage. Healthier crops grown from treated seed result in better stand establishment, improved crop vigor, strong, healthy root systems, and subsequently better yield. With the potential for a lighter environmental footprint, seed treatments use lower use rates and have less potential for off-target impacts. By applying directly to the seed, you are reducing the application of pesticides over the agricultural landscape. And by improving a seed's potential to germinate, growers obtain healthier, more productive plants using less seed per acre. Farmers have been treating seeds in order to protect their crops since ancient times. Early seed treatments focused on disinfection and techniques to preserve stored grains. Some of the first recorded seed treatments used sap from onions, leek juice, and wood ash. Salt water treatments began in the mid-1600s, and the first copper products were introduced in the mid-1700s. Other key milestones include the introduction of arsenic in 1740 and the introduction of mercury in 1915. These last two products were subsequently banned after more than 60 years of use, after their toxicity to humans and the environment were better understood. Fungicide seed treatments were introduced in the 1930s and targeted fungi that destroy plant cells and tissues, prevent seed germination, and cause poor development or death of seedlings. Some of these diseases may not kill the plant outright, but can affect a plant's architecture, which in turn can increase a crop's vulnerability, including to weather-related damage from wind, water, or drought. The earliest fungicides were broad-spectrum, like organic mercury, thiram, and captam. However, these products were also damaging to the environment and human health. The first systemic seed fungicide, carboxin, and the first seed treatment to control airborne diseases, triazole, came along in the 60s and 70s. The newer generation of fungicide seed treatments came in the 1990s with the introduction of fludeoxonil, azoxystrobin, and sidaxane. These products are still in use today. They are considered broad-spectrum fungicides, and they have very low use rates. The first insecticide seed treatments were those used to control insects that attacked seed during storage. This was followed by the introduction of lindane in the 1940s to control soil insects like wireworms, and then organophosphates in the 1950s, primarily to control corn maggots and thrips, but other insect pests as well. More modern insecticides came along in the 1990s as well, including neonicotinoids like imidacloprid, thimethoxam, and clothianidin. This new class of insecticide seed treatment offered broad-spectrum and systemic control, similar to what had been developed for the control of fungal pathogens. Neonicotinoids when introduced, were originally categorized, according to the EPA, as reduced-risk pesticides because they were considered to have minimal impact on the environment, were safe to workers, and highly efficacious. Now, 22 years later, and with implications for many crops, neonicotinoids are making big headlines. They are being reevaluated by EPA to better understand their application and efficacy, their impact on pollinators, and the possibility of risk mitigation to protect non-target species. If neonicotinoids are removed from the market, there will be an impact to modern agricultural practices and implications for integrated pest management programs that use these pesticides to protect their crops. Other types of seed treatment amendments are also evolving to protect seeds and enhance seed viability. These include nematicides, plant growth regulators, and biological seed treatments. The first seed treatment nematicide was introduced in 2005 on vegetables. Nematicide products are now registered for use on cotton, corn, and soybeans. Plant growth regulators are plant hormone-based products that assist in normal plant functions. Also known as PGRs, these chemicals alter the growth of a plant or a plant part. While historically PGRs have been around since the 1930s, their use in seed treatment technology is fairly new. Lastly, biological seed treatments. These are microbial organisms that can mitigate the effects caused by insects or diseases. If used in combination with fungicides and insecticides, they can enhance the level of control offered in a seed treatment product. Biologicals typically occur in and around the root system of plants and offer added protection as the root system grows. In modern seed treatment, often the final coating added to the seed is a polymer. Polymers can improve the coverage of the total seed treatment mixture on the surface of the seed, aid in the application of biological seed protectants, establish a barrier between the chemistry on the seed and the handler, reduce friction and abrasion during storage and planting, reduce dust, and improve the cosmetic appearance of the seed. Another benefit of polymers is at the commercial scale. Polymers help to protect against the buildup of treatment materials inside seed treatment equipment. Regulatory authorities, seed distributors, and growers have high standards for seed treatment technology. The expectations are that the treated seed will be easy to plant, effective in the field, and safe to applicators and the environment. Seed treatment needs to provide added value to the seed in the form of better emergence, higher seedling establishment, improved crop health, higher yields, and improved quality. Seed treatment is designed to optimize environmental safety and sustainability. There is room for growth, and as you will hear from both Amanda and Paul, many tools that are used to understand the science behind the new technologies that are being developed. Seed treatment offers safety to growers and applicators by reducing exposure during handling, reducing dust during storage and planting, and provides a focused area of application on a seed-by-seed basis compared to spraying pesticides over crops. Seed treatment has allowed growers to reduce the amount of land that is tilled, maintaining nutrients in the soil for longer and reducing erosion. Finally, seed treatment products are efficacious and offer both below-ground and above-ground protection from pests and pathogens, while introducing lower use rates and putting less chemicals into the environment. We should use our historical knowledge of chemical pest control specifically as it relates to seed treatment technology and strive to make better products that will support a changing agricultural landscape. With a focus on understanding how seed treatment can and will fit into integrated pest management programs that optimize crop protection and promoting safe products for both humans and the environment. Thank you. That completes my presentation.